Hello, everybody. It's your old friend, 𝗗𝗢𝗪𝗡𝗟𝗢 here, otherwise known in some circles as A-Team, and we are looking at the anatomy of a Dreamcast hack. I would consider this the first chapter or first installment, I guess with no real promise that there will be any others. But what I'm trying to provide here is some basic outline on how we can use tooling available today to do things like debugging, RAM memory, inspection, and assembly hacking. This won't be a deep dive into things like texture modification or writing custom tools to unpack and repack things like, one-off proprietary custom archives or containers. But I think this area here that I'm going to be covering is a huge delta or gap in the documentation and tutorials currently out there, and I think it'll prove quite useful. So we've actually started here with a simple emulator and cheat engine, well, the cheat engine called Cheat Engine. Now I'm actually using Demule because it's a very tried and true Dreamcast emulator. And in fact, for reasons that will become clear in a little while here, it actually does something really great when we start using it for memory inspection and then later have to translate that, no pun intended, over to the actual address, the memory address that the Dreamcast itself is using for that data. So here I've actually loaded up 𝗗𝗢𝗪𝗡𝗟𝗢𝗪, the project that I am so close to finishing at the time of recording this video. And this is the Japanese version, as you can tell. I'm not using any of my modified stuff here. But what I've done is opened up Cheat Engine, as I mentioned. Now what I'm going to want to do with Cheat Engine is actually open up my emulator process, Demule here. And I'm going to want to set my memory scan options here, starting at 2C000000. And the stop address can really just be, maxed out like you see there. And what I want to look at today is maybe different parameters or variables the game uses to render the font. Things like the tile spacing, the line spacing, whatever we can really find. Because I figure, that is probably an area of interest to most people who are looking at doing translation patches and such, is the font, right? So what I'm going to do here is start a brand new game. Now, as our new game loads, we're going to wait until the very first instance of dialogue text that we encounter, which will occur in just a moment here. We're going to make sure that pause when focus is lost is enabled on the emulator. Okay, starting to render text. Now, for purposes of this video, I happen to know ahead of time the way that the 𝗗𝗓𝗪𝗡𝗟𝗢𝗪 text rendering functions work. But in many cases, you will find games that sequentially load each font tile as it displays the glyphs, as it displays the characters and the dialogue text there for you in-game. And that sequential display, in 99% of cases, at least in my experience, means that we can isolate some value in memory that is going to say, okay, we're starting with character 0, then going up to 1, to 2, to 3. In other words, like a character counter. And with that character counter, the idea being that if we can isolate it accurately and we know that it's been identified, we can usually look around that space and hopefully find other variables or other parameters the game is using to make other dictations as to how the font should be rendered, how tiles should be rendered, etc. So as you heard me mention, right, I enabled the pause when focus is lost option there inside the emulator. Very crucial for a lot of what we have to do, right? We want to make sure we kind of snapshot the game in place. And I switched over to Cheat Engine. Now, Cheat Engine is something I have never used for any other purpose in my life other than developing translation patches for the Dreamcast. So I'm sure there are power users of this application who may laugh at some of the ways I'm about to use this, but I don't know. It's working for me. So as you can see, right, in the emulator, game started to render. Some tiles are being written to the screen. Now, here under scan type, I'm going to select unknown initial value. 4 bytes is fine. In most cases, especially on the Dreamcast, usually a single parameter is going to consume 4 bytes of memory. In some cases, it's actually less, but let's just go with the default of 4. All these other options here are fine to leave at default. So we'll do first scan. Now, of course, we're not expecting to get anything back, but now what we can do from here is click quickly back over on our emulator, return to Cheat Engine, more tiles were rendered. Let's select increased value. Not increased value by, although that would be useful if you know to look for an exact increase, like let's say you're looking for where the game might store things like health or something of that nature. You know exactly how many numbers by which a value decreased or increased. But let's look at increased value. Click next scan. Oh, well, we've got tons and tons and tons of results here. We're obviously going to need to start narrowing this down. So back to the emulator, let it render some more. Increased value, back, let it render some more. Increased value, next scan, right? We just keep doing this. Okay, so actually we've reached the end of this particular dialog box. So what we're going to want to do now, let's say we let the next one run. All right, so at that point, it's not going to be an increased value from the last, right? It's going to be probably less, but we can tick the compare to first scan box. And if we do that, we're going to be able to continue to filter the results down. Now I'm going to uncheck that because now we can keep looking for increased value per our last relative scan. All right, so we do have a lot here. I'm going to give it just another go. Okay, that's the end of that dialog entry. Let's add a few things that look like they're anywhere within range. And as you can see, ignoring all of these library matches here, there really isn't much that could potentially be a hit here if we're looking for like a tile or character counter, unless of course it's doing things like storing this as a float. But let's kind of keep it simple here. I see these two, and these look like they could be something. So I'm going to double click them and add them to my my saved memory list below. And here is really great where we can give these names. We can change the data type, right? Okay, so going back to the emulator. Well, we can see that once the dialog entry finished rendering, those changed to 78. Let's hit a new entry. Oh, it looks like it's counting up. All right. Yep, and when we hit the end, it jumps up to 78. All right, let's take a look here. Let me say, what if we try to lock either of these? Oh, and look at that. So as we can see, it's no longer writing each sequential character. It's actually getting stopped right there at number 4, number 5, hovering around there because we locked this variable inside of Cheat Engine. So let's say I were to unlock. Oh, and there it goes. It continues. So now, why don't we start inspecting the area in memory around these particular values that we found? So we'll look at the first one, browse this memory region. All right, well, we've got a few parameters here, not a whole lot, and a bunch of, these aren't even going to be pointers necessarily. This is some sort of index of actually textures that are contained inside of specific archives that hold the game textures. I want to look at this one, the second one. Okay, well, this second one is a lot closer to what I'm expecting to find. Really just a quasi-isolated list of, these 4-byte parameters. Now, let's say that I've, okay, identified what I believe to be this character counter here. How might I go from there to finding the parameter or the variable responsible for dictating the amount of space between each rendered font tile, so that I could modify the game to use a narrower, let's say, for example, half width or variable width font? Well, you would likely want to, well, not likely, you would want to extract the font sheets, find them, identify them, and of course, start to do things like measure the default, kind of standard height and width of each font tile that the game, uses in its kind of vanilla state. But for a quick and dirty here, because this is for video purposes, let's say I didn't do that. Well, how about I take a screenshot right here, and I don't believe you'll be able to see it on screen because I'm using a tool to grab a region of the screen. I'm going to take a screenshot of a particular region right here inside of the emulator. Now, because of the fact that Demule uses a pixel-perfect kind of rendering window, we know that once we paste this screenshot elsewhere, we're actually going to get the the proper dimensions or resolution, rather, for said content. So right here, we can do something to potentially, kind of guess or even determine for sure the spacing of each tile, at least the width of each tile. So let's say I were to start with our first character on the left here. Right now we're at a, let's see, vertical width of 22 pixels. Well, we can see that the character before this starts immediately, and this character ends and gives us 1 pixel of space to the right before the next one. So 22 pixels could be it. It could even maybe be 21. Let's see if there's a way we can kind of make this determination. So starting at the left, 22. Yeah, I mean, 22, if you look at it, 22 seems to be a very, very solid pixel width. Yeah, I mean, it's even, all the way up into the end. So, all right, like I said, quick and dirty, let's say 22 pixels in terms of tile width. That's what we're going with. All right, let me get rid of the GIMP here. Well, those of you who can do quick hex to decimal conversions will probably notice we've got a few 22s here. And for those who maybe aren't sure exactly how we get there, well, we can open up our calculator in Windows or really anywhere, and we can take a look at decimal 22 and see that it translates to hexadecimal 16. So why don't we add these to our address list behind us, the same one we use to keep track of that tile counter. All right. So let's release the lock on the on the character counter there. And I'm also going to disable the pause when focus is lost option because I want to see these changes in real time. All right, so we have our first one here. Let me just move these windows around so we get a better view. There we go. So we've got our first one here, 22. Now I can choose to edit this in hexadecimal or a decimal, but let's just make it easy. I'm going to change this to 11. Okay, well, that had nothing to do with what we wanted. That also seems to be some type of character counter or something. Let's look at the next one. Well, by golly, that was the proportional scaling of each tile. So actually, 22, if I change it to 20, they just get a little scaled, a little narrower, but that's not exactly what we're looking for, right? We don't want to mess with the proportional horizontal scaling. We rather care about the spacing of the tiles. Well, let's look at this one here. Change it to 11. And that is the vertical scaling. And eureka, look at that. That is the tile spacing parameter right there. Put it back to 22, even up it to 23, 24, and as we can see, our changes are reflected in real time because of the way the main function just keeps executing and all of that. Awesome. All right, so we've definitely made some progress here. Now what we're going to move on to doing is, well, basically figuring out how do we take this address that we see right here inside of Cheat Engine and translate it to the address being used by the Dreamcast accurately, 100% accurately. Because I can tell you right now, all you got to do is change this 2C to an 8C, and in seems like 99% of cases you've got the correct address. But I want to show an actual, quote-unquote scientific method, a surefire method, because I actually did encounter one game that did use a custom base address, a more scientific method to find this, and I think you'll think it's pretty cool. But before we do that, we are going to want to extract the data from the disk, the GDI or the GD-ROM RIP, so that we can do some comparisons for this base address calculation. So there's a number of ways to do this. I'm going to just do what's visually the simplest to kind of demo or show. Obviously, if you're working on a project like a translation patch, you're going to want to streamline a lot of this process, do a lot of scripting, leverage all of the command line utilities for this. But we're actually going to use a kind of simple little GUI here called GD-ROM Explorer. Great utility by the legendary Japanese Cake. Awesome hacker. And all we have to do really is load up our disk image inside of GD-ROM Explorer. And I could extract just the game binary, which has already been bold selected here for me, because that's really all we need to do to look for the base address calculation. But since the ultimate goal in this video is to at least make one small assembly hack and then write it back out to the disk image, why don't we take the entirety of that disk image and extract it right here? So while this is extracting, I'll explain that I set up a basic directory structure here with the original GDI, the extracted GDI files, which are right here. I've got this boot sector directory where I'm going to extract out ip.bin, the initial program containing all types of metadata and some proprietary code to actually launch our game executable. And I've also got a little batch script in here to rebuild the GDI, but that will come later. So very good. We can close GD-ROM Explorer. We've got the files extracted. Now let's move on to figuring out that base address calculation. All right, so we've switched gears here. I'm actually inside of a virtual machine here running Ubuntu, and I've got the LXtreme Nitro emulator running, which actually has a full step-by-step debugger with breakpoints and some basic memory inspection features as well. Now, it doesn't have full compatibility with the entirety of the retail Dreamcast library. Maybe newer versions have fixed it. I actually need to compile one of the updated builds. But what we want to do here is once we have the game actually launched and running, well, we can open up the debugger, either click Jump to PC, or we can just pause at any point here. And we want to take a look at just a couple of instructions, or rather like a handful of instructions. So let's say right here, starting at this particular address. All right, we've got that going. Let's open up our game executable in a hex editor. I'm using 010 editor here, which I prefer. And what I want to do is actually search for, let's say, something that'll be a unique hit. Let's look for these 6 let's see, 1, 2, 3, 4. Yeah, let's say these 6 or 8 bytes, right? So we'll do 018B, 04A0, E3, 6C, 18D3. And we got one hit, as expected. And we have the offset or address at which that string of bytes was found. Now, we see the address as Dreamcast understands it here. We see the address, starting or counting at 0. Now, how can we calculate the offset, or rather the base address that Dreamcast is using to load this particular game into memory? Well, very easily. Let's take what we see inside of LXDream. Okay, and let's subtract from that the offset inside of our hex editor. And there we have it. And yes, as I said, this is the base address in the vast majority of cases, but just to be sure and to not lead anyone astray, so they're banging their head against the wall when nothing's making any sense, we wanted to calculate this in a very, very guaranteed, surefire way. So there is our base address. And now that we've got that, we can safely close all of this. Let's shut down our virtual machine. And our next step will be to start looking in Ghidra, a very, very powerful and very awesome disassembler. All right, why don't we clear some space here for our screen real estate. And we've got Ghidra open here. And remember, our extracted game executable right here. We just copy that path. So inside of Ghidra, we will start a new project. Default of non-shared project is good. Let's give this a location. So actually, I'm going to put it here. Great. Now we want to import a file or an executable. So, as I said, first read.bin, our game executable here. Let's bring it on in, and we need to set some options. It's not going to automatically determine the type of processor that this was compiled for, but it is the Super H or SH for the Little Indian, or rather Endian, not Visual Studio, just default Little here. And now for our options, this is where that base address we calculated comes into play. So if we copy and paste that and get rid of that space, we are good to go. Click OK. Open this up. We are going to get the code browser view from here. And we're going to want to perform the auto analysis. Sorry, just making sure I had nothing selected there. All right, so auto analysis will take place. The default options are just fine here. And let's go. All right, now that our auto analysis or disassembly of the game executable is done by Ghidra, we're actually going to see here inside of my code browser tons and tons of disassembled sh4 that we can sift through and have at. Now, obviously, for those who've never worked with assembly, this can be very scary or daunting or downright confusing to look at. But we're going to try to narrow this down. This is not going to be, like I said, a boil the ocean tutorial here, but just to kind of get people started, especially those who may have experience on other consoles. Now, back over on the cheat engine and emulator side, we can say, all right, we've identified the base address at which to load, the actual executable within Ghidra, so that all address calculations, both relative and definite, are going to be accurate. We've identified an address in memory here that contains the tile spacing value. But how might we actually find inside Ghidra where such a reference is taking place? Now, one thing you could do is just copy this value, minus the 2, of course, because we have to replace it with an 8. You could go into Ghidra and actually try to access that address. But of course, it's going to be out of range as this is in RAM. But in some cases where it's actually writing different parameters and values is inside of empty space inside the game ROM. But in our case here, we want to actually go back over to Cheat Engine and take a look to see if we can figure out maybe what functions or function is writing to this address. So this isn't going to be as good as a full-on debugger designed for this particular console, but it is pretty cool. So within Cheat Engine, we can actually create either breakpoints or just kind of these little sniffers here to see, all right, what kind of things are writing to this address, or rather just reading from it. But let's check out the write. Well, upon each rendering of a new dialog text entry, you can see we have one hit. Now, most of these addresses don't really do a whole lot for us, but we do see this here. Now, if we were to go check this out inside of Ghidra, well, what we've actually got here, and I can tell you this from the benefit of having worked on this for for quite some time now, is basically I would call them the font RAM functions. In other words, it's a 4-byte space in memory where the various functions that are responsible for rendering text and dealing with the font are going to get called from. And there are many, many, many here, right? So from this point, it's basically a trial and error, finding any and all functions that write to this particular address, figuring out which ones are maybe responsible for adjusting the font tile spacing inside of dialog boxes, which ones dictate that spacing inside of various menus, right? So in the case of 𝗗𝗢𝗪𝗡𝗟𝗢𝗪, I can tell you there's over a dozen. And these over a dozen functions are responsible for text rendering all throughout the game and the various different screens you can come across. But as they say, giving the benefit of hindsight, I will tell you that the specific location where our memory address here is being written for the in-game dialog text tile spacing occurs right here. So if we remember, looking back over at Cheat Engine, our address right here, C4176E8, well, there she is. Now, when we do these assembly hacks of this kind, they are never, never ever going to be this easy. I guess I got lucky for the purposes of demonstration in this video today. What we're about to see actually is pretty easy. Now, granted, all of the time it would take to isolate and find this particular chunk of code is going to be, very time consuming. But once we get there, we can see that there is going to be a particular value read in from this register here, or into this register here, R2, and pushing R2 into this place in memory. Now, if we want to just say, all right, well, let me put my own value into R2. Let's put decimal 16, or rather decimal 11 into that, so we can push that into RAM where the font tile spacing is stored. We could, but we may want to take a look around to make sure that overwriting that register isn't going to break something further down. Remember how we saw there's the same exact value used for the tile's horizontal and vertical scaling, as well as the tile placement. So again, benefit of hindsight, and having worked on this for almost 2 years now, I will tell you that this one part of the game right here, which may or may not have been hand selected for the purposes of this video, actually requires that I don't do anything special. I don't need to find some empty part of code where I have to jump and do all kinds of other instructions and jump back. We get very, very lucky, and literally I believe this is the one place I ever got lucky in this game's assembly where we don't have to worry about overwriting a register. We look at R2 here. R2 gets pushed to this particular address, which is going to be our font tile spacing. And then after that, R2 is not used again, except here where a particular function is loaded into R2 and then executed. So we're very safe to just modify this directly. And in fact, let's do something else as well. Why don't we give this value here, this RAM address, a label? So we can call this RAM font tile spacing. We'll append the address there. And from then on out, we can actually find, let's say we were to right-click, references to this particular RAM value all over the game. And look at all these places where it's being written. So if I were to be, working on a thorough end-to-end assembly hack of this game, I would need to make sure that any and every place where this font tile spacing parameter is being read or written to is conforming to my needs and reflecting the changes I need to make to this game. But as I said, demonstration purposes, it just so happens that all we have to do is modify this. And what do we have to modify? Well, rather than moving this 4-byte long stored at this particular address here into R2, we're going to turn this into something as simple as moving B hexadecimal 4 decimal 11 into R2. We can even see the pseudo C code on the right-hand column over here changed. And now that we've made that alteration, press O so that we can write this executable back out to the disk. So I already populated this with the path to our GDI extracted folder. Overwrite it, yep. Okay. Now that we've done that, it's going to be time for rebuilding our disk image and actually testing to see if our changes were reflected, or rather if our changes worked. So let me close our emulator here. Let's go back to our file browser so we can see that here is the new executable I wrote out to the disk just a minute ago. And our build GDI bat file, very simple. And no, I do not use Notepad for my daily text editing. This is for your benefit so you can actually read what's on the screen here. And it's quite simple, really. All it's using is build GDI, pointing at this GDI extracted folder, pointing at the boot sector ip.bin, and telling the game, or excuse me, telling the command where to write out the modified disk image. And that's it. So we'll go ahead and run this. And we can see that our new GDI is being built. And when it's done, it'll be time to test. All right, and the build is complete. So we want to fire up our emulator once again, load our disk image. Let's even go ahead and reopen the emulator inside of Cheat Engine. Keep the current address list because we'll be able to see also here before our very eyes, as well as the visual evidence of the text being rendered differently if our changes worked. So we've started a new game just as we did when this tutorial started. And let's see what we get. So right now on the left in Cheat Engine, we can see all those values are still set to 0 because none of the text or font initialization functions have run. But as soon as the first instance of text is rendered, they will. Hey, Eureka, there we go. Tile spacing of 50%, 11 pixels wide rather than 22. Of course, it's a jumbled mess. We can put this back to 22, and hey, that's what we expected to see with the vanilla game. But as we can see, our changes took place through that simple, literally 2-byte assembly hack. Now, I'm sure you have the the question of, well, what on earth would I be doing with this jumbled mess of text here, right? The idea is that you would want to be modifying the game's font sheet, which could be stored in any number of bizarre one-off formats. And believe it or not, this game stores them in the PlayStation TIM format, of all things. And I can find no evidence that this was originally targeted for PlayStation as a port over from PC back in the day. But make of that what you will. The idea here being, not to get off track, is that you would take that font sheet, modify each and every one of the tiles on there so that you would use something narrower, something that gives you more screen real estate for English text. And after doing so, using this modified width, you would have something that allows you to put that English text in nice and cleanly. And, really that's the story here. So in summary, we were able to use Cheat Engine to isolate and identify different parameters or variables being used inside the game. We were able to look at the 𝗗𝗢𝗪𝗡𝗟𝗢𝗪 debugger to do a quick calculation to determine base address. Once we had that base address, we were able to load the game executable into Ghidra as an SH4 little endian binary. And using the base address that we calculated previously, we were able to look for references to this particular address of this variable we isolated here, this font tile spacing, and we were able to make a very simple and, of course, convenient for demo purposes one-line assembly hack so everybody could see how this kind of thing works. And, of course, we rebuilt the disk image as well. So this represents something of a crash course just so people could potentially get their feet wet and cut their teeth on a process that's really under-documented. And before I wrap up here, I just want to give a huge, huge thank you and a whole lot of credit to Vincent NL from Naomi Mods. He's working on the Rent a Hero English translation patch as we speak, very, very near to completion. And he's done a lot of great work on the Dreamcast and, of course, the Naomi. And this method here using Cheat Engine, really, it was something I'd say pioneered by him for purposes of Dreamcast, and discovering that 𝗗𝗪𝗪𝗡𝗟𝗢𝗪 is really, really good with the way it kind of preserves, Dreamcast memory addresses and that whole block there. I have experimented with, let's say, for example, looking at like, what is it there with RetroArch, Redream, Flycast, that's the one. I have experimented with other emulators that give you benefits like fast forward and things, which could make hacking and testing a lot more convenient. But it does seem like they may not be as accurate when it comes to preserving RAM memory. So this method here with 𝗗𝗪𝗪𝗡𝗟𝗢𝗪 is really the way to go. And that being said, I hope everybody enjoyed this video. Hopefully it was educational. You learned something from it. And, by this time next year, we're going to have a dozen new Dreamcast English translation patches out there. Everyone, thank you for watching, and I will see you next time.